Thank you, Yang. Thank FIP for the invitation. So this is a little bit different from the bio work, but I do see a little bit of connection, as you'll see in one slide. So I'm going to talk about how we manage solar and mid-IR, which is our thermal radiation dynamically. So the motivation is really about energy, right? So the fact that we are right here, I suppose everyone is in front of the laptop indoor, and you can see this is the pie chart that we are part of the energy consumption, right? This is HVAC consumption, 70% just for us sitting indoor comfortably. And the reason why we need to spend so much energy on HVAC or heating AC is because without that, there will be a lot of problem, especially health issue, right? So if you don't have a thermal comfort, your productivity will decrease and your immune system and all kinds of disease will come after this. This is why we need to spend so much energy. So, but we are living a energy crisis or climate change crisis that we need to introduce more and more clean and renewable source to reduce the carbon or fossil fuel centric energy source. So the solution, this in my opinion, is up to in the sky, right? We can first of all see we have solar heating providing us free, clean heat source. Right? On the other hand, there's radiative cooling, which is a less familiar to us, but it's actually a very powerful technique. Also, a lot of exciting publication in the past few years. So here's how it works, right? So if you look at the heat balance of the Earth, which is where we are at the surface of the Earth, a heat balance between the sun and the deep space, right? This is where we can actually reach heat balance with. So you have the sun that's shining sunlight under the surface. So this is one heat source. You actually have a cold source because we have a temperature that's higher than absolute zero, so we radiate thermal radiation all the way to the deep space. Right, so this is we're actually dumping our radiation to the universe. Right, and this is a free cold sink. Now the concept of radiative cooling is pretty simple. If you can block all the heat gain, which is only the sun, right? The sun is the only source in the universe that's hotter than us. If you can block the sun, and if you can maximize the radiation coming from the Earth to the space, then you can actually achieve cooling that's actually below ambient, because we are now exchanging our temperature, exchanging our heat with deep space, which is much colder than what we are right now. So that's radiative cooling. And my question or my research is really trying to answer these two questions. Can we use both heating and cooling? And can we switch it just like what we do for HVAC? Because that's what we really need. We have seasons, we have different demands. We need heating in the winter, we need cooling in the summer. Right? So these technology alone cannot be complete. So this is just some math that give you an idea of what we are trying to tune. I just wanted to focus on these two parameters. This is emissivity, which would determine the amount of radiation that emit from ourselves to the universe. And this alpha absorptivity, and I specify this is in solar regime. So how much you will absorb the sunlight. And these are just a lossy term that you lose through the convective or non-radiative heat source. And then the question is, okay, what kind of material we need? What's the property we need to achieve so we can have a switchable solar heater and radiative cooler, right? So another terminology right here is Kirchhoff's law, which basically tells you how much you emit will equal how much you absorb at that particular wavelength. So at thermodynamic equilibrium. So apparently, based on the heat balance diagram that I just show you, for ideal radiative cooling, you want to minimize the solar absorption, right? You have the very, very small solar absorption right here, and you want to maximize the amount of emission in the mid-infrared regime, which is where we radiate at. And of course, this is a solar radiation. The shady area is solar radiation, and this is the transparent window of our atmospheric layer. And on the other hand, when you try to engineer a solar heater, you actually want to do the opposite. You want to maximize the absorptivity, right? And you want to minimize the amount of thermal radiation heat loss that's going to the universe. So this poses a challenge because we're talking about completely different and very wide band property, and that has to be tunable dynamically. So this is the objective of what we're trying to do, and from material science point of view. The next requirement that we want to achieve is that we actually wanted to have electrochemical tuning for several reasons. For example, if we use electricity to drive that, it doesn't have any moving part, and it's continuously tunable. And based on the commercially available smart window that we know, this is compatible with our building system. So I call this adaptive solar heating and radiative cooling, or ASHAR. Basically, what that means is that you can do the heating by dumping the heat to the universe. Do the heating by absorbing the sunlight in the winter, or do the cooling by radiating to the universe in the summertime. So a few material science design criteria I want to introduce, share with you. The first challenge we had was to engineer a ultra-wideband transparent conductor, because here's how an electrochromic or electrochemical tunable device works. It's just like a battery, but instead of focusing on storage, we're focusing on the property change in the solar and midnight regime. The first requirement is we need to have this top electrode that can transmit all the light, all the optical property change of this material. So it has to be transparent for both solar and midnight hour. Now, the first material that came in everyone's mind would be ITO, which is the commercially available, very well developed transparent conductor. Unfortunately, it's not transparent to midnight hour because of the plasma frequency is just too high. Some silicon wire, I don't want to go into the detail, but it didn't work either. So actually look into graphene. And the reason for graphene is graphene has this very unique energy band structure, which give you a very small, or give a very constant absorption coefficient, which is 2.3%, and all the way from visible light, which is somewhere in here, all the way to mid-infrared. All right, this is a very unique property of graphene, monolayer graphene. So we think this is great. And in order to provide a long distance conductance, we also add some metal grid to provide long distance conductance, and the PE film as a transparent support for both visible and midnight hour region. So in the end, you can see that this is transparent in the visible light regime, and also in the mid-infrared light regime. And the peak you see is from the polyethylene absorption. So that was the first challenge we need to solve. The next one is what exactly chemical reaction we're talking about. How do we actually create such a tunable device? So we look into the working principle of solar absorber, right? If you take out your solar absorber, take a TM image, you'll find those nanoparticles of metal embedded by some dielectric. So this is called ceramic metal. So the reason why those how this metal nanoparticle works is it's based on surface plasma resonance, which has certain resonance frequency. When you have a lot of different particles, a lot of different distance, you have a lot of different absorption frequencies that will give you a broadband absorption. And in infrared, those metal behave like a continuous film. So it behave so it's highly reflection in midnight hour, which will give you a low absorption because it's opaque and therefore low emission. So overall, this ceramic or nanoparticle structure give you a selective solar absorber, and that is high absorption here and low emission in the mid-infrared. So we have that, and now we just pin them together, right? So this is how our working principle is. If you need heating, then you apply electricity to the transparent conductor. All right, so now we'll start to deposit silver. We use silver nanoparticles, and these will start to do the solar heating. And when you want to do the cooling, you reverse the bias, dissolve the nanoparticle back to the electrolyte, which is transparent to sunlight. And now the sunlight will reach all the way to the bottom, and we have the silver back reflector that will reflect the sunlight. And the electrolyte is actually a very good thermal emitter. So right now, this is doing a radiative cooling, right? And I also want to emphasize that we put some platinum on the surface of this transparent electrode for catalyzing the chemical reaction. And the electrolyte is the MSO. If you're interested, this is the electrochemical reaction. So this is the property, right? Because first of all, you can see the trend is correct, right? So we have a higher absorption for heating, but lower emissivity for heating, and the cooling is the opposite. One thing I want to emphasize is that we haven't demonstrated sub-ambient yet because the solar absorptivity is too high still, and this is our future work. So spectrum aside, this is what will be probably more intuitively useful. So if you look at the thermal image, when you see the cooling mode, you see a lot of radiation coming out, give you a higher apparent temperature. And in the heating mode, all this radiation is suppressed, so you see a colder apparent temperature. That means just have less emission from the device. And in visible light, you see in cooling mode, it behave like a mirror. Right? And in the heating mode, it's just a dark light absorbing material. So we can, of course, dynamically tuning this by reversing the bias back and forth. Again, I want to emphasize the tuning is the opposite, it's the right way. And we are achieving, the cycle life is not that good yet, about 10 cycles. And we attribute those cycle life decay mainly due to the loss of platinum, which I'll be talking about very soon. So that was our first attempt to demonstrate this solar mid-IR tuning device. Our unpublished work, we switch from silver DMSO to copper in water, and for several reasons. First of all, it's safer. You don't want your building to catch fire when you use organic electrolyte, and it's cheaper. And this is so the electrochemical reaction is more stable when you switch from to copper aqueous. So in the interest of time, I'll just go real quick in this one, but it's the same working principle. But here we first focus on the mid-IR first because it takes several more steps to do the solar part. So we focus on the mid-IR, and we found that the electrodeposition is actually a very, very good tuning mechanism to give us a very, very large contrast in the mid-infrared regime. So as in comparison, this is some literature we found. We actually have one of the largest tuning range. And I just want to mention that the maximum is from 0 to 1. So 0.85 is actually pretty good. And we also try to study why the platinum is so good. Because without platinum, you cannot have a good adhesion or a good affinity between the metal and the electrode. So we collaborate with Venkat from CMU to do density functional theory to prove our point that when you have the platinum on the top of the graphene, you can actually create a more uniform coating that will actually be beneficial for mid-IR tuning. And we also use effective theory and Fresnel equation to explain that indeed, when we deposit metal, we can actually use this effective theory to predict why we can have emissivity switching. So we haven't have a good characterization tool. We haven't had a characterization result about the porosity, so we just fit with a different kind of porosity. But in general, they have a pretty good agreement that we can indeed treat the metal as a uniform film when we try to understand why the emissivity keep decreasing when we deposit more copper. And of course, in addition to the optical, we also want to see how much thermal regulation it can actually give us. So we have this environmental chamber. When we change the temperature, we can adjust the voltage to make it either high emissivity or low emissivity state. The bottom line is comparing to a single functional surface or static surface, we can maintain the heat loss when the ambient temperature is fluctuating, which is what we want, right? So when it's winter or summer, it all give you the same thermal comfort. And again, this is without any additional energy input, because we don't need to we don't need to supply energy to maintain the state, just like a battery. So in the end, I want to demonstrate that we also try to do the modeling that give us the we can estimate energy saving for the entire US map. You can see it's mostly favorable for some part of the US. And that's also give us a good understanding of what we can do in the future. So in the future, if we can really demonstrate sub-ambient cooling, and by suppressing the solar absorptivity, we're looking at a annual energy saving about 20%. And comparing to just mid-IR, which is 60, we are talking about 350 energies mega BTU per year. So in the end, I want to acknowledge my students. The work that I talk about today is mainly done by Chun Hsu, Yunfei, and Xiuqiang, and all my fund agencies and collaborators. Thank you very much.